Hello. In this tutorial video, I will discuss some important things to keep in mind when using concave solid surfaces. For example, let's say we want to simulate a meniscus inside this vertical solid cylinder. The direction of gravity is opposite to the z direction. In the experimental settings, I have already enabled the gravitational force, setting realistic parameters. All the other settings are set to their default value. We now add the fluid interface mesh to represent the meniscus inside the cylinder. We select the built-in circular flat mesh, selecting 2.5 mm as its radius, since this is the radius of the cylindrical tube, and we load it. By showing the mesh normal arrows, we see that they point towards up. So, the fluid below the interface is the lowest fluid in the current view. The Young's contact angle, formed in the fluid below, is set to 60 degrees. So we expect a meniscus with its concavity towards up. We select the cylinder as constraint for the fluid interface mesh boundary. And we are ready to launch the equilibration. The equilibrium shape of the meniscus is as expected. I will now repeat this same exact simulation. So, I first remove this fluid interface mesh. Then, I re-add the same initial fluid interface mesh we loaded before. I select the cylinder as constraint for the boundary. This time, however, before launching the equilibration, I disable this option. When this option is enabled, the equilibration is executed with a constraint that all the edges of a boundary should maintain a similar length. If I now launch the equilibration with this option disabled, you can see that something goes wrong. The reason is that now, the edges of the fluid interface mesh boundary are no longer forced to keep similar lengths. So, because of the concavity of the solid surface mesh, the fluid interface mesh can create large gaps between its boundary and the solid surface to reduce the fluid interface surface area. However, these gaps are unphysical. They are an artifact of the simulation model. By enabling the option that forces all the edges of a boundary to keep a similar length during the equilibration, the formation of these unphysical gaps is prevented. So, this is why that option I showed you should always be enabled when using concave solid surfaces. Let me now mention another important remark about concave solid surfaces. Let's say we want to simulate a droplet wetting this solid surface in between these two vertical pillars. I use the default values for all the equilibration settings. So the option to force all the edges of a boundary to maintain a similar length is also enabled. I now add the fluid interface initial mesh to simulate the droplet in between the two pillars. The Young's contact angle selected for this solid surface is, inside the droplet, 60 degrees. Finally, I select this solid surface as constraint for the droplet's boundary. And we are ready to launch the equilibration. However, also this time something went wrong. The cause is again the concavity of the solid surface mesh, in particular, the presence of these sharp edges, and the fact that the fluid interface initial mesh had only 4 vertexes along its boundary, so the simulation was not able to correctly detect the shape of the solid surface. Let's now repeat the same simulation. but using a slightly more refined mesh as initial mesh for the fluid interface, which I can create by selecting the finer boundary option. This initial mesh has more than 15 vertexes along its boundary, so the simulation should now be able to correctly detect the shape of the sharp edges. So, let's try it. I select the solid surface as constraint for the droplets boundary, and then I launch the equilibration. As you can see, this time the equilibrium shape of the droplet is computed correctly. The small gaps between the fluid interface's boundary and the sharp corners of the solid surface are gradually reduced while the mesh fineness is increased. Let me now discuss a new option that was introduced from the version 1.0.2 of Interface Equilibrator, since this new option is relevant when using concave solid surfaces. This new option can be found in the equilibration settings, and when it is enabled, it ensures that, in any case, the elongated facets of the mesh along the mesh boundary will be refined. That is, such facets are split, regardless of the other settings regulating the mesh refinement. So when the mesh boundary is constrained on a concave solid surface, this option helps ensuring that the mesh boundary remains sufficiently refined during the equilibration. To see the utility of this new option, let's consider, for example, the following configuration. Here we have a vertical solid cylinder with radius 1 mm. Then a circular meniscus inside the cylinder, with its boundary constrained on the inner side of the vertical solid cylinder. And another flat meniscus outside the cylinder, with its inner boundary constrained on the outer side of the vertical cylinder, and its outer boundary constrained to move only vertically to mimic a flat interface far away from the cylinder. In the experimental parameters, gravity is enabled and the capillary length is set to a typical value for a water-air system, that is a few millimeters. Because of Jurin's law, we expect the meniscus inside the vertical cylinder to rise to a height dictated by the cylinder's radius and by Young's contact angle inside the cylinder, which in this simulation is set to 60 degrees. I recall that Jurin's law states that the capillary rise h of a meniscus inside a vertical cylinder is given by this equation, whereas the cylinder's radius, theta, is Young's contact angle, and L is the capillary length. So, since these are the values we set in our simulation, we expect a capillary rise of roughly 7 millimeters. Let's then try the simulation. As I said in the beginning, this is a good example to show the utility of this new option. Indeed, here I select a very low value for the maximum number of vertexes to allow the mesh refinement, because I want to keep the mesh of the meniscus inside the cylinder poorly refined, so that it can quickly reach its equilibrium height. However, because the mesh boundary is constrained on a concave solid surface, I also want its boundary to remain sufficiently refined to avoid problems, and this will be ensured by this new option. Let's then launch the equilibration. And as you see, the meniscus inside the cylinder is rising, as expected from Jurin's law. And even though its refinement remains low, due to the settings we selected, its boundary remains sufficiently refined, so no problems arise due to the solid surface concavity. Now that the meniscus has reached its equilibrium height, we can check if this is the value predicted by Jurin's law. And indeed, the height of the meniscus is around 7 millimeters, as expected. Now that the meniscus has reached its equilibrium height, we can launch a new equilibration to further refine the fluid interface mesh. And this is the result. So to conclude this video, let me summarize the important concepts to keep in mind. When using a concave solid surface mesh as constraint for a fluid interface boundary. Firstly, in the advanced equilibration settings, remember to keep enabled the option to force all the edges of any fluid interface mesh boundary to maintain a similar length. Secondly, keep enabled also the option to refine, in any case, any elongated facets along the mesh boundary. And finally, ensure that the fluid interface initial mesh is sufficiently refined along each boundary constrained on a concave solid surface mesh. Thank you for having followed this video. For more information and for other tutorial videos about Interface Equilibrator, please visit our website.